There are two marbles in this cup. One is white and the other is blue. If I close my eyes and pick a marble, what are the chances I'll pick blue? My eyes are closed and the cup is shaken in between each draw, so the chance of getting white or blue is random. There's a 50-50 chance of getting one color or the other. The same principle applies to genetics. With a plant that is heterozygous for flower color, there's a 50-50 chance of it giving either the white allele or the purple allele. The chance of inheriting any given allele is random, and this randomness lets us make some really cool predictions about what traits will show up in the next generation. I'm Science Mom.
And I'm Math Dad.
Today we're talking about Mendel's first law of inheritance, segregation.
And we'll teach you how to make Punnett squares.
Hello and welcome! I see the McLeods in Minnesota. Hello to Catherine in Houston, to the Hall family in Ottawa, Alafia and Pippa watching in Texas, to Annabella, and to Brian in Chattanooga. Today we're learning all about probability and Punnett squares. Math Dad's super excited because today has some math. Let's do a quick review of some super important terms though. If you do not remember these, make sure to go back and watch our previous lessons again. So when we're talking about organisms, we can talk about the phenotype. That's what we see. So these flowers are purple and these are white. That's the phenotype. Okay. But we can also talk about the genotype.
Ooh. So there's always two alleles.
Yes, two alleles. And for the purple flowers, the genotype can be either two copies of the purple allele or a white copy and a purple copy of the purple allele. So it can be heterozygous or homozygous. Those are two other words that we learned. So we have homozygous traits and heterozygous traits. With homozygous traits, we see the same alleles. And with heterozygous traits, we see different alleles. And the trait that we see, like purple flowers, can either be dominant or recessive. And how do we know if it's dominant or recessive? Well, it's by looking at the heterozygous case. When we have two copies of the allele that are different, the trait that shows up is dominant. So these are the terms that are super important to know when you're talking about genetics: homozygous, heterozygous, genotype, phenotype, and dominant recessive. They're new words that we don't use all the time, so if you're feeling a little confused about them, make sure to go back and review and do the worksheets. You ready to dive right in, Math Dad?
I'm ready. We're talking about cats.
We are. So if you knew that the length of fur on a cat was a Mendelian trait, and you knew that either long hair or short hair was dominant, how would you find out which was dominant?
Ooh, I know I've seen a lot more short hair cats.
Well, the only way to know and to find out is to do an experiment. So if we have a long-haired cat, and this long-haired cat is homozygous because we have a pedigree going back generations and we can see that all the ancestors of this cat were long-haired, and then we have another cat that is short-haired, and the same thing. We have this purebred cat. We know that all the ancestors had short hair. If they breed and all of the offspring are short-haired, what does that tell us?
Oh. Well, in that case, if we ended up with short hair is dominant, right?
Yes, that would tell us that short hair is dominant. And this is what we would know from doing this cross.
Was it important to know that they were purebreds?
Yes.
Okay.
And if we saw the opposite result, that all of the cats had long hair, then we would know that long hair was dominant.
Right.
And if you had a mixture with some having long hair and some having short hair, then you'd know that your cats weren't necessarily purebred. And in reality, this is a Mendelian trait, and what we see is that short hair is dominant. So actually, Math Dad, when you said most of the cats you see have short hair, that happened to match.
Right.
But is the dominant trait always going to be the most common one?
Oh, we talked about Munchkin cats on the previous day, and having the short legs, that was actually the dominant trait.
It is dominant. If you breed a Munchkin cat with another cat, then that trait of Munchkin legs is actually the dominant trait. But do we see most cats being Munchkins?
No, so the recessive trait is actually the most common in this case.
It is the most common. So just because something is dominant, that does not mean it will be the most common trait in a population. What if you had a dominant mutation that was super dangerous and anybody with that mutation was going to die really young? Would that trait then be the most common trait in the population?
No, it would not.
Absolutely not. But oftentimes, the dominant traits are more common. Now, to understand genetics, we need to talk a little bit about probability and the first law of genetics, which is the law of segregation. That means that if you have two alleles and they're different, the chance of getting one or the other is going to be 50-50. So here, blue is going to represent our dominant allele.
Okay.
Yellow is going to represent the recessive allele. And Math Dad, you and I are both going to close our eyes. You got to shake the cup and then pick one out without looking.
All right.
And 50-50 chance I'll get blue. I got blue.
Oh, yellow.
And Math Dad got yellow. Now we're going to fill in this little chart here real quick. And this is similar to the chart that you could be filling in on page 22. And you don't have to use marbles. You can use anything as long as you can tell the two of them apart. So you could take
popsicle sticks would work well.
Popsicle sticks, a piece of paper with a letter on it. There are lots of different things you could do.
Okay.
So let's do it again.
I'm ready.
We're going to do it 4 times.
Blue.
I got yellow.
Okay.
So we got the same result here, but we each pulled out different things than last time. So I'm going to fill that in real fast.
Okay.
One more time. This time,
I peeked.
Math Dad's cheater pants.
Yellows.
I got yellow.
Okay.
Did you peek and then did you close your eyes
No,
again?
I did. I re-shook it.
You redid it.
That's right. I would never cheat.
And we got homozygous recessive. Now we're going to do it one more time. I got blue and Math Dad got yellow. Now, it's important to understand that just because the chance is 50-50, that doesn't mean that you're going to get a perfect distribution. So like flipping a coin, right? 50-50 chance it's head, 50-50 chance it's tails. Does that mean that you're always going to flip head and then tails?
No.
No, you could flip heads twice in a row. You could flip tails twice in a row. Same thing with our law of segregation. The distribution of the alleles is random, and if you do enough of them, you will see an even distribution.
Okay, so on average, things are going to work out. That makes a lot of sense. And so we were kind of simulating 4 offspring in that cross.
On average, with this cross, where you have 2 heterozygous traits being crossed, on average, you're going to see about a quarter will be homozygous recessive.
So yellow, yellow.
Yellow, yellow.
Wow.
And about a quarter are going to be homozygous dominant.
Blue, blue.
And then almost half are going to be heterozygous.
That's right, because if you just list all the orderings, you could do blue, 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 yellow, yellow, blue, and yellow, yellow. And all 4 of those are equally likely.
That's right. And this is what gave Mendel that 3-to-1 ratio, because he wasn't looking at the genes. He couldn't see the chromosomes. He couldn't see the alleles. He was just looking at the phenotype. And when he looked at the phenotype, he saw that 3-to-1 ratio. So this activity on page 22, I want to make sure that you do it. You can pause the video right now and give it a try, or you can wait till the video is done and come back to it. But take your objects and then close your eyes, draw one out at random, and then write down what you get. Let's do just one example, okay,
sure.
Math Dad?
You could even roll a die, do evens versus odds or things. Yeah, there are lots of ways of simulating this. All right.
Okay, close your eyes.
I'm ready.
All right, we got blue and blue, so we are going to write AA for homozygous dominant there. And then you would keep going and you'd fill out the whole entire chart. You're gonna do it again? All right.
I'm having so much fun.
Heterozygous for our second one.
All right.
And the more you do, the closer you'll get to that ratio that you expect if the chance is random. And this leads us to how to do Punnett squares. Now with a Punnett square, we're not saying, okay, we did it 4 times and here's what we got. With a Punnett square, we're showing what the results will be on average. We're doing the probabilities.
So Punnett was an individual who first kind of formulated them this way.
That's right. He came up with this. So for the parent over here, we're going to divide the alleles in half. And it doesn't matter what order you do it. You can put capital A on the top square, lowercase a on the bottom. Doesn't matter. What's important is that you are splitting them up evenly. There are 2 alleles, and we've got 2 rows or 2 columns they can go into.
Wait, what if you put blue on top and purple on the side?
Doesn't matter. You'll get the same results.
Okay.
And now that we have split up our alleles like this, now all we need to do is just copy them down through the square.
Okay.
So we get capital A here and here from the purple parent. We get lowercase a here and here from the purple parent. And now it's time to do the same thing with blue. Okay. Lowercase a across the top, capital A across the bottom.
Ooh, and once again, the order didn't matter.
Order didn't matter, except, and our results are that here we have homozygous recessive, 1/4. So what was the chance of getting homozygous recessive?
1 in 4.
1 out of 4.
So when we do a heterozygous cross, and the phenotypes would be in a 3-to-1 ratio.
3-to-1 ratio, exactly what Mendel saw. And I want to give a quick shout out to Ames and Shadowmation. I'm seeing lots of 1/4 and 25% in the chat. Good job, Amira. That's exactly right. So with a heterozygous by heterozygous cross, this is what we see. 1/4 are going to be recessive. The other 3 are going to look the same. They're all going to look dominant.
The phenotype.
For the phenotype, but we have 1 that's homozygous and 2 that are heterozygous. Let's do another one.
Okay.
And the only way to get comfortable with these is to practice. We have 2 pages in the notes that you can practice, and after you watch this lesson, you've got to fill those out and get some practice.
Okay, so what is the chance of little b, little b? Let us know if you've got it figured out. All right, so Science Mom.
So first we're going to split up these alleles, put 1 in each category.
Big B, big
Same
B.
thing right here. Capital B and little b.
Okay.
Then we just have to carry them through and write them out. So I have a big B here and a large B here, little b, and now I do the same thing with the green parent. With the green parent though, I don't have an option. It's just big B no matter what.
It's kind of a little bit boring almost, but yeah. So overall, how many little b's did we get? 0.
0. Good job, Dancing Slippers and Monica and Riley and Veronica. 0% chance of little b. And I have a little example of this, Math Dad, that I think is sort of funny, if you can make us big real fast. So if I have capital C for confetti and capital C for confetti, and you have to pick one of them, and it means that you'll get, and capital C means you'll get confetti dumped on your head, what are the chances you'll get confetti dumped on your head?
Well, I can only choose capital C.
100%. So when our trait is homozygous, there really isn't a choice. If I have a cup and I just have, 2 blue marbles in the cup, what are the chances I'm going to pull out a blue marble?
100%.
100%.
Yeah, you don't have any choice.
And that's how it was with this homozygous trait here, this capital B. The only allele it can give is the big B. There's no other option.
So that makes sense. And an interesting thing with these probabilities, we're actually kind of multiplying them. So to get little b, there's a 1/2 chance of, and 1 times a 1/2 chance, that actually works out to be 1/4. Or if we wanted to count the number of possible things, if there are 2 options for the first parent, 2 alleles, and 2 possible alleles for the next parent, 2 times 2 is 4. And that's one reason why when we do these crosses, they use the letter X, because we're talking about multiplying.
We are. So what if we have homozygous by homozygous?
Ooh, so little d cross big D. What is the chance of getting capital D, little d? So the homozygous cross, but then what's the chance of getting a heterozygous offspring?
So for this one, there's only one option of what we can give, right?
Yeah, it has to be a little d.
Same with the purple. There's only one option of what we can give. And if we fill out this entire Punnett square, It's all the same.
Oh, man, this one's almost a little boring. They are all the same, but
Yeah.
we took two homozygous cross homozygous and we got nothing but heterozygous offspring.
100% heterozygous. And I'm seeing the chat just fill up with 100%. Good job, Three Amigos and Elmo and Rebecca and everyone else, Catherine.
Nice.
It's the exact same as if we did this. So make us big real fast. If we have homozygous, with blue being dominant by homozygous recessive, we're going to take one out of each cup.
But there's no mystery. We already know what's going to happen.
No matter what, we're always going to get a heterozygous. On page 24, I believe, there are some Punnett square examples you can do with little aliens. And having one eye is our recessive trait. Having two eyes is dominant. So with this cross right here, what's the chance of seeing a one-eyed alien?
Ooh.
We have a two-eyed alien by a one-eyed alien, and just like before, what I need to do is split up these alleles. And it doesn't matter what order you put them in. You can have the big B on the bottom or the top. And I'm going to do the same thing for my one-eyed alien. Put this here.
Okay.
What are we going to see? Maftad, tell me what they're saying in the chat.
All right, they're saying 50%, 2 out of 4. And I agree. We do indeed get 2 out of the 4 that are little b,
Exactly.
Homozygous recessive.
So these will be one-eyed aliens, and then these ones will be two-eyed aliens. So there's a 50% chance of having a one-eyed alien from this cross. These are pretty fun, aren't they?
Oh, they really are. And I wish we could actually see genotypes. Unfortunately, we can only see the phenotypes. So I could see that the alien has 2 eyes, but I don't know necessarily whether it has capital B, or capital B, lowercase b, so whether they're homozygous or heterozygous.
But you always know if it's a recessive trait, right? If you see a one-eyed alien, then automatically you know, aha, this genotype is little b because it's recessive.
So sometimes you can see genotype.
Sometimes you can. It's pretty cool. A real-life example here, back to talking about cats. With cats, there's white cats and there are black cats, and it turns out one of those colors is a dominant color. Which do you think it is? If you had a white cat that was purebred and a black cat that was purebred and you crossed them and they had kittens, what would you see? Would you see all white cats or all black cats? What do you think, Maftad?
That's a good question. Have I seen more black cats or white cats in my life? Black?
It turns out that white is actually dominant.
Ah.
And black is a recessive trait.
Oh, and that's why you chose the W for the allele letter?
That's right. It's tradition usually to pick whatever trait is dominant, and the first letter of that word is often the abbreviation, but we could use anything. We could use A's and B's if we wanted to. But here I've done W's, so make sure when you're writing this out that you write your capital W really big and your lowercase w really small so you can tell the difference, because they're not super easy to tell apart. Okay. And then up here, we have little w, little w.
And your question is, will there be black kittens?
Yes, and I want you to answer that question before you do the Punnett square. And it's okay if you're wrong. If you mark one of these with your guess and then you end up being wrong, that's okay. But I want you to think about it. Will there be black kittens? Yes or no? What do you think, Maftad?
Okay, well, the only way to get a black kitten would be to have little w. So can that happen in this case? And yeah, I think you can. You're going to guess
yes? Yes. All right, let's fill it out and find out. So first we bring our big W across, then we bring the little w across. Now we do the same thing for the other parent, and this one is little w's all the way across. Do we have black cats?
We do have black cats, and not only some, but half the time.
Yes, about half of the kittens will be black cats from this cross.
Right, and that's on average. There's always a chance that it just wouldn't happen at all, but yeah, we would expect about 50% of the offspring to be black cats.
So going back to our cups, Maftad, if yellow represents our black cats and blue represents the white, this is what this same cross would look like. Ooh. So if we try this, close your eyes, shake it up, and pull one out, are we going to get a black cat?
Black cat.
We did. Yeah. Remember, because yellow is representing our recessive.
That's right.
So let's do it one more time. Did we get a black cat?
Mine's boring. I'm not even going to close my eyes.
That's right. You don't need to close your eyes.
Another black cat.
Black cat again.
Keep going till
we'll do one more.
White.
Now we got white. All right. One last thing before we finish, I do want to mention we've had such good questions and we haven't had time to answer them all in class. So on Teachable, if you log in, look under the lesson and you will see answers to questions that we didn't have time for in class. Like a couple times ago, Isabel asked, I'm the only one in my family who can't roll my tongue. How does that work? What, is that genetic? And we answered the question in Teachable. So make sure to check that out. And now it is time for our What's That Critter mystery.
All right. I know.
Math Dad thinks he'll stump you, but I think this one is a little easier. I bet you're going to get this one really quick.
We shall see. Oh, no. Did that just happen?
That just happened, Math Dad.
Aw.
I guess we can go backwards.
Maybe. Yeah, I don't know. Do. I'm sure they all had their eyes closed. This critter lives on the plains of southern Africa. And,
Spoiler alert, it's a springbok.
they've been clocked at 55 miles per hour. Clue number 3. They can leap 3.5 meters high and can long jump up to 15 meters.
That is amazing.
That is very impressive. It's a springbok.
It is a springbok.
Oh man, look at that. The chat, you guessed it right.
Good job.
How did they do that?
Ibrahim and Micah and Isaac and Colleen and everyone else who wrote springbok.
How
That
did
was
they
really
do
funny,
it?
Math Dad.
I'm way impressed. You blow me away. All right, load faster. You can do it.
Time to go to itempool.com/sciencemom/live. It looks like we're having just a little bit of a technical difficulty, so bear with us a minute. Math Dad will try reloading it, and we will have our 5 poll questions.
All right. I can't tell if it... All right.
There we
error
go.
message, and then restart.
Cross your fingers with us, everybody.
All right. Well, maybe they don't need to see us.
There we go. We're back. We're back. Our first question is about a heterozygous trait. So
if you cross 2 animals that are heterozygous for a trait, all of the offspring will also be heterozygous.
is that true or false? So think back to that first Punnett square we did. If you cross 2 animals that are heterozygous for a trait, will all of the offspring be heterozygous? And Math Dad here, why don't you, let's represent it with our cups real quick. So 2 heterozygous individuals, that would be like we close our eyes and we're gonna both draw out at random from cups like this.
Okay.
What would you get?
Here we got one category clearly dominating.
It is dominating. I think the Unbeatable Science kids are gonna win this one, Math Dad.
It's not fully unanimous. There's some lack of confidence here. All right, finishing and revealing the answer to be false.
It is false because we could easily pull out heterozygous or homozygous dominant or homozygous recessive. All those possibilities can happen when you have 2 heterozygous individuals cross with a trait.
Okay, that was a good warm-up question. All right, take a look at this picture here. What portion of the offspring from this cross do we expect to be black? So this was...
How many black cats would you get from this cross?
So it would be 0%, 25%, 50%, 75%, or 100%. It's a very happy-looking cat.
And how do we decide which letters to use for a trait?
So I think you said we could actually pick any letters we want.
You really could pick anything. The tradition is to take whatever the dominant trait is, like for purple with flowers. If purple is dominant over white, then you would have capital P represent flower color. That's the tradition, but sometimes people make exceptions because certain letters, like the letter O, are really hard to tell apart from capital to lowercase. So if orange is dominant, usually scientists will pick a different letter because capital O versus lowercase o, they're hard to tell apart.
And sometimes you get like black and blue and they both start with B and you're like, maybe I don't want to do that because it might confuse me. But yeah, you have the flexibility, the freedom there. Okay, what do we say? It is a 0%
0%.
chance. So why would we get no blacks in this instance?
Because, if you'll get your cup ready for me, Math Dad.
Okay.
If we have black and white and they're both homozygous, then what are we going to get? Well, from this individual, we'll always pull this allele. From that individual, we'll always get that one. And the offspring will always be heterozygous.
It makes sense. Well done there. All right, our next question involves a made-up trait with these mushrooms. In this case, we made a Punnett square, and then we erased all the genotypes and instead replaced the genotypes with phenotypes.
Oh, that was sneaky, Math Dad.
So the genotypes would be the letters, the alleles. The phenotypes, actually what we're seeing, in this case, which of the following must be true? So blue coloring the dominant trait or the recessive trait, or red dominant or recessive? Let us know what you think.
So we're saying that this trait for mushroom color that Math Dad made up, it's a Mendelian trait. One is dominant, one's recessive. Can you tell which is which from this Punnett square? It's right here. Right here, Gallatin, on his shoulder. Nope.
Do you like my cute little mushrooms?
I do. Those are very cute mushrooms.
I didn't draw those. I just stole them, but they're cute mushrooms. And I've never actually seen a blue mushroom, but I would like to see a blue mushroom.
Mushrooms come in a lot of different colors.
Okay, I'm seeing 2 things get a lot of votes and 2 things get hardly any votes.
It's a sign that the Unbeatable Science kids are about to win, Math Dad. Let's find out.
I hope it's a sign that we're starting to feel comfortable with this vocabulary. And the correct answer is that blue must be recessive and red has to be dominant. And we know red is dominant because when red was what we got for all of the offspring here. And
that's the only explanation that works. So nicely done. Good job, everybody.
One of them had to be recessive, one of them had to be dominant because it was a Mendelian trait. But we're going to work with the same picture again, same scenario here where the genotypes got erased and only the phenotypes are displayed here. Which of the following must be true? This is a much trickier question here. So both of the mushrooms in the cross must be homozygous. All the offspring are homozygous. All the offspring are heterozygous. Or there's no way to identify the genotypes of the offspring. So take your time, don't rush through this, and we'll give you a little bit of time to think about this idea. No more easy questions.
Math Dad asked me if he could do some harder questions today, and I said we can do harder questions if I can make a mess, and he agreed.
So this hoping you would forget that.
This next question is even trickier, but it's a good one.
Love seeing the bars grow. And when I asked the question, it's kind of funny. By instinct, I just reached, what do you think? And I looked down at Kaladin because he's the only student that we actually see face to face here. No.
He's a very good student. Yeah. He thinks the Unbeatable Science kids are going to win. That's what he thinks.
Ever the optimist.
He also thinks that he wouldn't mind going back and taking more of a nap because he was sound asleep when I picked him up.
Oh yeah? This is the harsh world we brought him into in front of the lights.
I think we have a clear winner, Math Dad. Are you ready to reveal the results?
We do have a leading candidate here. All right, let us reveal the correct answers here. So what has to be true? Ooh, you did get it. Nicely done. So both have to be homozygous. How do we know that that's the case, Science Mom?
Because if one of them was carrying the other allele, then you would see a mix. So
in particular, we know the blue one. It's just recessive. It has to have both recessive alleles, but that means that if the red member of the cross had any blue allele, then we would get blue offspring, and we don't in this case. We only get red offspring, so they both have to be homozygous. So the red one is dominant for the 2 alleles, and the blue one is recessive.
Which means that all the offspring are going to be heterozygous.
Ooh, because that's right, because if you cross blue and yellow.
Or pretend like those are red for the mushroom.
Yep.
We're going to get
They're all going to be mixed. One of each.
All right, now it's time for the hardest question. Math Dad came up with a tricky one.
Okay, select each true statement here. The most common phenotype of a trait is the dominant version of that trait. The genotype capital A lowercase a and lowercase a capital A give the same phenotype. When you cross a dominant phenotype with a recessive phenotype, all the offspring will have the dominant phenotype. And the last one, a recessive phenotype must always have a homozygous recessive genotype.
Ooh, Now, don't go through and just mark all of them correct, because if there are any that have more answers than not, then Math Dad will claim victory.
And they don't get their confetti if they don't get them all right.
But they get an evil laugh, so that about evens out, right? And make sure to think about each one. Is it true or is it false? Then only mark the true statements.
Yeah, this definitely is a question you have to stop and think about. Sometimes we'll ask a question and you can just answer it as fast as you can click.
Other times you need to take a minute to think, and that's a good thing. Pause and think about it for a minute. You can even pause the video to give yourself a little more time if you want. So
Right.
the most common phenotype of the trait is the dominant version of the trait. Is that true or false? The genotype big A, little a, and little a, big A give the same phenotype. You want to read the next two?
When you cross a dominant phenotype with a recessive phenotype, all the offspring will have the dominant phenotype. And finally, a recessive phenotype must always have a homozygous recessive genotype. Do you like that pretty tree behind us, Science Mom?
I do. That's a good background. All right. Should we call the answers?
I think we're ready.
Let's find out.
Oh, you did get it right. Nicely done. Okay.
Confetti time.
So going over those answers really quickly. So the most common version of a phenotype doesn't necessarily have to
It's not
be the
always
dominant
the
one.
dominant trait.
So, like-
Often it is, but not always.
think of the Munchkin cats.
Yep.
And then the other wrong answer was that, yeah, dominant cross recessive doesn't always give you a dominant phenotype. Instead, if the dominant one is a carrier, you might indeed get the recessive phenotype.
Yep.
All right.
Good job, unbeatable science kids. Math Dad's got confetti for you, and then a silly video.
Anglerfish mating begins when the male anglerfish literally sinks his teeth into the female. He attaches himself permanently and lives as a parasite on the female's larger body. Eventually, the male is absorbed and used by the female to fertilize her eggs. It didn't work so well.
No, not something we recommend. Now, what we covered today, we're getting into like the real heart of genetics with learning about probability and then learning these terms that we need to be able to understand the concepts that are coming. So if you're feeling a little confused, make sure to rewatch the videos that we did before and to practice, fill out those worksheets. And just to drive our point home, if one of these cups is empty and the other one is filled with peas, Math Dad, split peas, what are the chances of you getting split peas dumped on your head if I say, all right, pick a letter, and whichever letter you pick, I'll dump it on your head?
Oh, wow.
So this
It's
is
going to be a 50-50 chance, right?
Yes, basic probability. If one of these is empty and one is full, there's a 50-50 chance. What letter should Math Dad pick?
All right, chat, let me know. What letter should I pick here?
Capital A or little a?
Did I really agree to this?
Yep, you did.
Okay, I guess I'm seeing mostly capital A's, so I'm going to pick lowercase a. Oh no, it's all down my back.
You should have gone with the chat and picked the capital A, Math Dad.
Oh.
And Kaladin is like, what in the world is going on? We hope that you enjoyed this lesson learning about probabilities, and next time we're going to be talking about the second law of Mendelian genetics, which is independent assortment. What happens when you have more than one trait? Join us next time to find out.
Work hard, grow smart, and we'll see you next time.